All right, to begin our discussion today on part design for cycle time reduction, we're going to discuss wall thickness, part removal, cooling, multi-material, and multi-cavity. Wall thickness. Let's establish a few key points that you should be aware of when working with plastics. Plastics are a great insulator and do not transfer heat very well. For example, we all know how well aluminum transfers heat. This isn't the case with plastics. So, in processing, what you'll find is that the outer layers tend to first insulate, and then the plastic within the layer will cool slowly. As a consequence, you'll observe that thinner sections solidify quickly, whereas thicker sections require a longer cooling time. Although many people instinctively know that a thinner part improves part cooling, what most people don't realize is that cooling time is exponential to part thickness. That is to say, it's not linear. Although this common cooling equation looks complex, it really breaks down to the following. Theoretical cooling time uses a few factors to relate the thickness squared divided by the thermal diffusivity of the material. In essence, every doubling in wall thickness quadruples the theoretical part cooling time. So to repeat, cooling is not linear, and the graph here shows that this nonlinear relationship, and also shows the difference in cooling between PBT, shown by the dashed lines, versus the polycarbonate ABS blend, shown by the solid line. Also keep in the back of your mind that both of these materials melt differently. For example, the polycarbonate ABS blend tends to soften as it melts, whereas the PBT type polyester has a very narrow melting range. These curves are characteristic of the cooling that you'll observe. In other words, you will note steep cooling characteristics on materials like PBT with a narrow range. Other examples of materials with a narrow melting range are nylon and acetal. What is also important about these curves is that they show the relationship between part thickness and wall thickness. With the PBT material, you can see that the conditions provide a theoretical cooling time of 5 seconds for a 2 millimeter thickness. When the thickness of the part is doubled to 4 millimeters, the theoretical cooling time is actually quadrupled to 20 seconds. So as a rule of thumb, every time you double the thickness of a part, it increases the theoretical cooling by about 4 times. In actuality, the cooling time will increase even more because the increased part thickness actually increases part shrinkage. With increased shrinkage, the outer part surface loses contact with the mold surface. This will decrease the efficiency of heat transfer from the part to the mold surface. This effect becomes even more obvious in semi-crystalline materials such as nylon and polypropylene that shrink as much as 5%. Adversely, less than a 30% reduction in thickness will cut theoretical cooling time in half. In practice, the actual cooling time will decrease even more due to the improved heat transfer. Additionally, a part with reduced thickness will fill faster, reduce less packing, and consume less material, thus saving time, energy, and resources. Now, to continue in our discussion on wall thickness, we are looking at a typical diagram for a rib design. This is what you'll find in most design guides. The cooling time of a rib is not just affected by the rib's thickness, represented by T. Most of these factors affect the cooling time of the molded part. For example, an increased radius at the base of the rib or increased draft angle increases the effective thickness at the base of the rib. In this representation, you'll note that we have simplified part thickness with circles. For those of you who've not been directly involved in part design, we can use these circles to represent the effective thickness of the plastic part in order to estimate cooling time. On the right-hand side, the diameter of the circle is the same as the wall thickness, while the diameter of the circle under the rib is approximately 30% larger. When using this circle diameter in a theoretical cooling calculation, the cooling time increases 70% over that of the main wall. So to sum up, we try to reduce variations in circle diameters in order to minimize sink, provide structural integrity, and to approximate the cooling time. To conclude this part of the discussion, cooling time is dependent on the thickest part of the part, increasing the importance of maintaining a consistent part thickness. Now we're going to discuss part removal or part ejection. With injection molding, cooling time is dependent on being able to evenly cool a plastic part and prepare it for ejection. In this example, we have pin ejection. I chose this example to illustrate a point. You'll note that with pin ejection, it quickly becomes complicated to route water lines. Basically, the more pins you add, the more difficult it becomes to add cooling lines. In reality, using a stripper ring or stripper plate would be the best way to eject this part, as it would allow us to locate adequate water lines very evenly so that now we can distribute ejection forces evenly across the perimeter of the part. When ejecting any part, it's important that we do not distort the part as it's being ejected or introduce stresses that will cause the part to deform in its application. This is why stripper ring or sleeve ejection is used to eject this type of part geometry. It may cost a little more for the mold, but the part would run a faster cycle time. Also, since the force is evenly applied around the perimeter of the part won't distort, and the likelihood of the part becoming marked is reduced. In some cases, we've seen the use of air ejection by using poppet valves or porous steel to assist the ejection of thin-walled parts. When you use this type of a system, the part will be ejected faster since the warm part is still soft and it blows off the core more easily. In reality, plastic parts are getting more complicated every day, but keep this point in mind. No mold design will ever compensate for a poor part design. Even though this seems obvious, we see hundreds of parts designed without consideration of how they will be injection molded in production. So when a part's not designed properly, we're forced to try to compensate through processing. And this usually leads to longer cycle times, compromises in part quality, just to ensure the part will eject properly. And this also takes away from how the mold will run in production. When ejecting any plastic part, it's imperative that you distribute the ejection force as evenly as possible. Remember, you need to overcome the force of friction and vacuum when you eject. Your part design must provide enough area that will allow some type of mechanical mechanism, like a pin or a stripper ring, to positively move the part away from the core. When you have to deal with undercuts, be sure to position in a manner which will best facilitate their removal during mold operation or part ejection. You must also allow enough space around the undercut for actions such as lifters and slides to properly move.